and NCIS have popularized the idea of forensic investigations. And if you're old, you remember the Quincy show, but I'm not sure how many of you remember that. In reality, forensic engineering, known as the investigation of failures, sounds like a lot of things in my life, is a complex, rapidly changing, high-level area of expertise. I think Tom's going to deal with something else. Our speaker today, Tom Crane, is a founder of Crane Engineering, part of ESI, and is a national leader on the topic of forensic engineering. Tom founded Crane Engineering in 1978, which is a consulting firm specializing in forensic engineering. Tom will share with us some exciting case studies and his perspective on the future of forensic engineering based on more than 45 years in the field. He started when he was 8. Including his expertise of fires and explosions. We're looking forward to a very dynamite presentation this morning. Couldn't resist, sorry. Please join me in welcoming Tom Crane.
Thanks. Well, it's hard to resist an invitation like that, so I guess I just better continue this morning. It is a pleasure to be here. We appreciate our connection with Dunwoody and each one of you today. So we're going to do sort of a Reader's Digest condensed version of a topic which has become very broad and very deep these days. As the introduction said, I've been doing this way too long. And you'll notice they've now given me a title, Principal Emeritus. Basically what it means is I don't have to wear a tie if I don't want to. So let's continue with it a little bit. First of all, at Crane Engineering, we're located right out in Plymouth, a few miles from here. We developed a multidisciplinary approach to the whole concept of forensic engineering. My background is mechanical, includes a bit of HVAC, includes a lot of machine design, many other things. My specialty in the last 25 years or so particularly has been the fuel gas industries, natural gas, propane, and incidents related to them. We'll see a couple of pieces representing that sort of work. Broadly, though, we investigate automotive incidents, be that crash analysis or vehicle technology failures. We investigate fires and explosions, carbon monoxide, structural failures, bridges, roof collapses. We have an extensive laboratory where we employ metallurgists, whom I've had other conversations. Metallurgists tend to be the most expensive roommates you can find if you're a consulting engineer because they need exotic toys, but they're useful. The metallurgists are, at least, and a wide variety of other things. So after many years, we were talking to a collegial competitor of ours, ESI, which allows us to expand across the country in our work and theirs. And this is just a little portrayal of a number of the major areas that we as a company work in. And we do this work not only nationally, as you see here, from about 16 different offices, but internationally as well. So let's talk about forensic engineering, because that's why we've got the billboard up today. I think one of the most interesting aspects of forensic engineering is a very simple fact. Something went wrong. Now, I cleverly created an interesting tie-in to today's date. 79 years ago today, we had one of the most archetypal, iconic engineering failures of the last century. The Tacoma Narrows Bridge, not far from Seattle, Washington, failed on this day in 1940. It had been in service since its completion in June of that year. If you're not familiar with the Seattle area, here's a quick map of Seattle, lower part of Puget Sound, which is near Tacoma. I've been over the current bridge quite a number of times. This was a bridge put up, remember 1940, we're talking pre-war. We were talking about a buildup of the Army and the Navy, both of whom had major stakeholdings in the development of this bridge to save a 10-hour drive to get to those areas instead. The challenge is that even during construction, this bridge showed a lot of dynamic motion, meaning it's flaying around when subjected to the wind. These iconic videos taken at the time of its failure show the behavior on the day of the failure incident 79 years ago today. Gusts in this area estimated to be 40 miles an hour and greater. It's extraordinary. If you had any engineering background at all, you will have seen these many times, and you've gone into the technical detail as to the aeroelasticity that resulted in a resonance that caused the bridge deck to do this, ending up with this catastrophic event. One of the questions I think that is so obvious that we may not ask is, why is that interesting? Why is it noteworthy? It's a huge amount of resources involved, to be sure, but there's another very basic reason that that becomes very interesting to us as lay people and certainly technologists. We don't expect engineering failures. That's not why we design things. We design them based on engineering principles. That means mathematics, physical property, materials is expected to have a foreseeable life, not that. Now, before I get to the next part, here's a trivia question, notably for anybody in the audience who has gray hair. This was 79 years ago, 1940, November 7th. What is the tie-in that Minnesota has with this event? That's a good try, but way off. The same storm that produced these winds, 40 miles an hour or more on Puget Sound, moved across the northern tier of the country. 4 days later, November 11th, Armistice Day, 1940, is the date of the great Armistice Day blizzard. Quite a number of people died. A friend of my father's was duck hunting on a Mississippi River on that day, barely escaped with his life. Many people died, same storm. So that's the Minnesota tie-in. It devastated the Midwest as it went on. Forensic engineering. I want to get through the graphics or the text stuff really quickly here to get some of the pragmatic stuff. The investigation of materials, product structures that fail or do not operate or function as intended. Is that because they were designed wrong or manufactured wrong? The field also deals with retracing processes, procedures leading to accidents in the operation of vehicles and machinery. Pretty broad, I guess we're all on the same page so far. Generally, the purpose, locate a cause of the failure and improve performance, or assist a court in determining the facts of an incident. Now this is pretty bland. I'll also tell you that the other thing that in court a forensic engineer is expected to do is offer opinions that is liable to assess liability for a given party, such as was the design defective and why. Now, one of the myths of being an expert witness is that basically you can go into court and say anything. When I started this work a long time ago, there was some truth to that. There were some flagrant opinions being rendered by engineers that were utterly inappropriate. The federal rules of evidence have changed dramatically over the decades. I won't go into this in a lot of detail, but Rule 702 basically says you have to have valid scientific methodology, valid scientific understanding of what's going on, or that will not be allowed. Testimony based on sufficient facts or data. Testimony is the product of reliable principles and methods, meaning it can be tested. And the person expressing that has applied the principles appropriately. Justice Harry Blackmun stated this succinctly: expert scientific evidence is admissible if reliable and relevant. And the focus is on the principles. How did you approach the case and the methodology? Further, pertinent evidence based on scientifically valid principle will satisfy the demands of relevance and reliability. That's background. That's the wallpaper that we do our work in. There's another element. 1995, the first edition of NFPA 921, and you may recognize NFPA as a body that promulgates standards through a vast area of fire protection work. It provided a document which is a guide for the investigation of fires and explosions. In those intervening years, it has become more sophisticated. This is a key central part. I'll let you look it up yourself. We don't have to go through every part. Scientific method should not be a surprise to anybody in this room. Our operations manager, not an engineer, a number of years ago said, "Why are we doing this?" My fifth grader came home from school and said, "We study the scientific method in school." I think what happens is we forget. This is a very basic procedural idea. Define the problem. Then what do? You collect the data, you analyze it, develop a hypothesis. What could have happened? And then you test it. Could that really have happened? Now, that's all what we work with. We have to abide by that. It can be simplified. What does it mean? What gets us into trouble is not what we don't know. It's what we know for sure that just ain't so. And I thank Mark Twain for that. And that means I'm going to this fire scene and I know they were smoking the night before. I'm just going to find the matches and that'll prove the whole thing. Okay. Let's talk about the actual work of forensic engineering. Now, I've got some studies, a couple of them involve fire. And one of the reasons that fire is a really good example, and this can be applied to vehicle accidents, aircraft accidents, and anything in between, you often start with chaos. This is a fire scene, fire and explosion. Not much fire in this one, but a lot of explosion damage. It is chaotic. It's very difficult to tell where the walls were, what happened first. What we want to do as a result of the investigation is build it backwards. Back in the day, I could talk about frames on a film. We'll just talk about frames on the video, coming back to the way it started. That's our goal. We have to collect the evidence from that chaos and make a studied and analytical perspective as to how it got that way, particularly when the event looks like this to begin with. In case you're wondering, we did not go out to this farm and give some business cards out before this happened. This is a test that we conducted along with the Minnesota Institute of Arson Investigators. One of the things that we did while we leaked propane into this building was provide a lot of instrumentation, thermocouples, pressure transducers, and notably, one of my favorites, an accelerometer that we placed on the first floor of this abandoned farmhouse, because we knew the floor would have uplift as a result of the explosion. We measured G-forces that went beyond the scale of our accelerometer in excess of 100 Gs, being accelerated vertically upward. These events, because of the broad area that an explosion works over, can be extraordinarily destructive. What happens next? We get to the scene. Why? Document, field test, and harvest the key artifacts. That means we take back to the lab things that are really important. One of the technologies available to us these days, and I won't belabor this because I think a lot of folks have become understanding of what 3D laser scanning technology can do. We do this so that in spite of the chaos, we could come back and understand the location of all things, dimensionally, their relationship, and so on. We also use drones. We didn't have to on this one because we were there when it happened. So when we then look into the cause of a failure like a propane explosion, we go from this stuff down to testing details. And for piping explosion, natural gas or propane, we clearly want to look at all of the piping. In this particular instance, we became aware that there was one particular joint that was of great interest to us. So the next step is lab inspection. We bring the harvested artifacts back to a laboratory where we can look at them in great detail. Now, everybody, including my introducer, talks about CSI, NCIS, and so on. I will tell you that the way that that has really changed our lives as forensic engineers is not in the depth and the quality of what we do, but in terms of expectations of the average juror. Because typically, we expect science to be wrapped up in about an hour, including commercial breaks. So yes, with this one instrument, immediately tells me that this, based on a full-level molecular analysis, this object was created on June 12, 1789 in Lyon, France, late on a sunny afternoon by a left-handed artifact named Jacques, right? Okay, it's not gonna happen. A typical case investigation may last several years, and you'll see why later when we talk about it's not just the artifacts, it's all of the other things that go with it. So, what is an artifact? This, from one of our cases, is a flare nut found at an incident. And you can see, especially in that central picture, there's a crack. I will tell you that that crack was the cause of a loose joint at that location. Now quickly, I can start to name the parties that would have been involved in a matter like this. Was it the installer that over-torqued it? Was it the manufacturer of the nut that had some bad brass, or what? So the next thing we do is we allow one of our people, which is, I call them the pathologists of our work, a metallurgist, to look and analyze that fracture. In other words, was it bad metal or something else? And to do that, you'll notice the pictures on the left, we have to cut up and section the component. As a result, before we do that, we document the condition of that in great detail. This is using a CT scan that will illuminate that crack that we see in the side of it so that we can convey what we are doing here, not only to our client, but to lay people constituting the jury or possibly a mediator. Again, why? In the end, we are telling a story. So in the end, I want to make you understand what I have learned with my knowledge and background without being so arrogant or presumptive that I could give you an engineering education in several different fields in the time of a few hours. So I will come to court with something like this to be able to show you what a flare nut actually is. By the way, has anybody ever seen a flare nut used in copper tubing here? Hands? Yeah, pretty common. Now the problem is, you may or may not have familiarity with it. You may not be able to relate to it. That's why storytelling is important. The following picture, I'm going to tell you a story. Can anybody think of the beginning of this story? How about the beginning? Okay, the middle, you remember the middle? The end of the story? It's all about porridge. The point of this simple picture is if we allow people to understand references from their world and their culture, the learning takes on a whole different dimension. Also, I want to be able to convey my thoughts as an engineer as the steps went along. So you remember the picture that I had when my metallurgist was slicing my nut, flare nut apart? It no longer looks like that, but because I did a CT scan, I could use 3D printing technology and create the equivalent in a 3D printed version that I could sit, if you're on the jury, I could sit here now and talk about this crack that we found, and now it makes sense. It may not have for that small device as to how that could possibly have happened. A very specific example of this happened in our office about 3 days ago. One of our senior engineers was being deposed, and that's a process where he is grilled by opposing attorneys on his theory of a case. The case had to do with an industrial facility which had gone through a very damaging and fatal explosion and fire. Part of the factory was a very, very large drying oven where very large components would be subjected to heat lamps to dry paint. There was a large door on the front that they would wheel the equipment into. And our engineer was making the point that there were discrepancies in the witness testimony as to whether the doors of this drying oven were closed at the time of the incident or not. His assumption, based on other engineering data, is that they were closed. When he was cross-examined, the attorney was saying, "You can't possibly know that. John Doe said he knew that they weren't." Our engineer says in response, "Well, there's also a certain logic. If I'm baking cookies at home, I not once have ever left the oven door open. It doesn't make sense." He took it to a level that a jury or a mediator can understand immediately by using the cookie analogy. So in the end, we want to be able to explain this happening in great detail. This continues. Before the dust settles, let's move to a case study. A carbon monoxide fatality. In the country that we live in, northern United States, this is all too frequent. The one that we are going to look at happened on January 25th of 2005. The location was Plymouth, Massachusetts, right on the Cape Cod area near Boston. Very unusual weather for them at that time of year. It was a blizzard. There were winds clocked in excess of 60 miles an hour that day. And during the course of the storm over 3 days, there were 3 to 4 feet of snow generally in the area. I'll tell you going into this that the location of the incident was a residential house, not particularly old, about 5 years old at the time. Very few modifications by the owner with one exception. They had built a deck low to the ground out the back of their house. This was also the location where the exhaust and intake for a propane-fueled boiler was located. That was the source of the heat for the house. The husband in this family was a snowplow operator and maintenance person for the city. So during the storm, he was gone a large part of the time. He came back and he found that his wife, who was expecting a baby, was comatose, and their 8-year-old daughter was deceased. Here's the picture of that side of the house as investigators first looked at it. That's the area of interest right there, and that's the exhaust and intake from the boiler inside the house. I will say immediately, investigators concluded that what must have happened, since it was known that the power was out for a number of hours during this storm, clearly this exhaust and intake must have been covered by snow. When the power came back on, it started up and must have hollowed out like a snow cave within it, thereby trapping the exhaust products. That was the theory from literally the first day. So most incidents are a combination of statistically testable components and stochastic events. You want to be a hit at the next party, throw around the word stochastic. This is a picture of the boiler in that residence. You'll notice the exhaust and intake goes straight up in that central flue and then out just above the foundation level. This is a picture of what we created in our lab over here in Plymouth. The challenge we found when we simulated the exact theory that had been put forth on this from the beginning is if you completely blocked the exhaust from this system would shut down. That's what it was supposed to do by design. So we added the ingredients that we knew were present at the time. On the left, you'll see a picture of our exhaust system at our laboratory. We have thermocouples set up to verify temperatures of the exhaust. And on the right, you'll see 2 very large fans that we had. We couldn't generate 60 miles an hour, but we were able to get a steady 45 miles an hour exhaust air impinging in that direction, exactly congruent with the incident. And the lower part is where we added snow from our own parking lot. So a quick mention about carbon monoxide. There's carbon monoxide in this room right now. It's not affecting anybody. Carbon monoxide is a toxic component that you have to have enough of to really be a problem. OSHA states that the level of carbon monoxide to be an immediate danger to life and health is 1,200 parts per million. A properly operating gas appliance is allowed by code to have up to 400 parts per million in the exhaust. There's nothing wrong with that. It's being exhausted. Most appliances run at a level of about 10 or 12 parts per million. Bear that in mind. When we put all of our laboratory testing together, including Minnesota snow, this is what we observed. You'll notice the recirculation that's happening. What we observed is that this effect created carbon monoxide buildup being drawn into the boiler intake, and the levels were in excess of 20,000 parts per million. The cause of the incident, therefore, became readily identifiable. Without the wind, Also, without the deck that the homeowner had built that close to the exhaust, without the snow, without the intermittent snow that had stopped for a while and then started up again, this would not have happened. The players involved in the litigation clearly were the homeowner and the family who had suffered the fatalities, and also the installer, the manufacturer, and several other parties related to the inspection of the device. It was noteworthy. The tragedy of this incident led to Massachusetts invoking a carbon monoxide requirement in their building code. Now, larger, complex issues require a number of different experts. You will see this in the next case study. I used to believe that you only needed a mechanical engineer to basically solve any problem that you faced. I learned that from my father. That obviously is a simplistic untruth. The reality of today's experience is that we need to link the disciplines during the course of investigation to thoroughly understand without leaving an important assumption out of it. So, if you have a small team, it's a straightforward investigation, probably a small economic loss. A large team, it's just the other end of the scale. Complex investigation and large economic loss or serious injuries. Team of experts. This has become more common for large loss investigations. Think of any large loss that you can, 35 Bridge going down and any others, that's what you will find. It allows each expert to be focused on their area of expertise, and they can stay in their lane, which is, I'm not going to talk about plastics because that's not my field. I know about them. After all, I'm a mechanical engineer, but it's not my field. So if I have a polymer scientist next to me, we can do work together. It adds a diverse perspective. That should be obvious. Now, what kinds of technical expertise do we typically see involved in these civil litigation issues? I'll let you read it off really quickly. Well, there it goes. It's everything. And there's far more than this. One example that I'm particularly fond of, we were working on a case a number of years ago, and having nothing to do with the work that we were doing, there was an issue as to whether a handwritten note about the proper care of a piece of equipment was brand new or old. It was stated that it was old, this handwritten note telling the people how to take care of a particular piece of equipment. And the allegation is they didn't follow that instruction. Turns out there are such things as ink aging experts. I had no clue. So they were able to analyze, to me that gets very CSI-like. To me, they were able to analyze the ink on the handwritten note and say, this couldn't have been more than 6 months old at the time it was written, thereby completely taking away the argument that that was there and available for years. So as the case progresses, and I've already given you a snapshot of going from a scene where we may need documentation technicians and other experts all the way to a laboratory and then producing exemplar devices. The first look, particularly at a fire, and I'll emphasize this for this next case study, it may be a first look, origin and cause expert, overall assessment, then a second look for safety, subrogation potential, joint exam, joint scene examination, identification and retention of artifacts, collecting the data, followed by the lab exams, followed by testing. So it's not uncommon for a large loss to start to look like this in terms of the team of players. So here's our next case study. This also occurred in the Midwest, not Minnesota, but a nearby state. And in the winter, the subject is a very large egg-laying barn fire. This was one of the engineering drawings portraying part of the schematic. So overview of the incident, and where are we on this? First, what's the problem? January 31st, 2014, upper Midwest, severe cold weather. 4-alarm fire of a major structure, a chicken barn for over 300,000 birds. This barn was about 100 feet wide and 500 feet long. Happened at night. The structure burned to the ground. This is a picture taken by a news helicopter as the fire is in progress. It was well involved early on. very little any firefighters could do to really extinguish it before it was a complete loss. There were no fatalities in this, aside from the livestock that was in it. But if you can imagine, the economic loss on this was extraordinary. Multiple millions of dollars, both in the livestock, the building, and so on. The building, curiously, was fairly new, like about 2 years old at the time. So this is the barn in question. This is what it looked like after the fire. Remember the chaos that begins these things? That's where it is. This is the electrical room in the barn in question after the fire. Now, I'm going to ask a very simplistic question. Why would we be interested in the electrical room? Yeah, all of those guesses get to the fact that electricity is a power source. Looking at fires, you need a power source. You need ignition, you need fuel. So of course, you're going to consider the electrical along the way. This is exciting, I need water. So that's what the electrical room looked like. Again, we ran a 3D laser scan of this. This is sort of a presentation format flyby. It's convenient, it gives the portrayal of the entire scene. But actually, when these become useful, it's when we can actually go down into great detail and once again measure distances. We can preserve the scene in case it turns out there was a contractor who was not even known about at the time of the incident, who's brought into the action a year or two later. They have the benefit of seeing exactly what we did. So what went into this team that we sent to the scene? Origin and cause, to be sure, for all of these reasons: patterns, witness statements, interviews. By the way, whether we're talking fire, vehicle accidents, industrial accidents, what you see there in terms of witness statements and interviews, that is typically very non-engineering kind of data. It's not hands-on, it's not measurements, it's not testing an electrical circuit, but those become vital in understanding the evolution of an incident. And engineers are not used to dealing with lay interpretations of what they see. So we also need, clearly, an electrical engineer for very obvious reasons. Equally obvious, we need a mechanical engineer. Again, looking at the power sources within the building and the location of those systems. And data forensics. It used to be, of course, data forensics didn't even exist as a field. Now it is invaluable because most of these systems are going to be controlled by a central programmable logic controller. To properly load that data without corrupting it, data forensics expertise is critical. And scanning techniques, digital documentation of the scene, be that drones, 3D scanning, and even photography that can be turned into 3D representations. So this is where we are collecting data under the scientific method. So what we do to do this is rule in or rule out potential causes. The gas or electric heat, none was present. In an agricultural system like this, it is common that the heat of respiration of the livestock, in this case chickens, is relied upon for heat. In fact, you're trying to get rid of that heat during the coldest days. Mechanical issues. All mechanical systems were off except the fans. If you want to follow this, remember the word fans. Electric process equipment. It was last used 4 hours before the incident. Lighting circuits, not on. So now we're analyzing the data to come to a better understanding of what we had at the scene. And notably, what I'm illustrating there is this is very interactive. We collect data, we analyze it, collect more, analyze it, and go on. So now we're ready for the lab exam. Why? We process the artifacts, collect the data, document, testing. And the experts here are the whole suite again. So we're at the point, and I say in this presentation, I'm only a few minutes into it, but this is about a year after we start, where we can start talking about developing a hypothesis. We have interview information now from a wide variety of sources. We also know the trip breaker patterns, fire patterns, building plans, product information, discovery materials. Product information, again, foreshadowing, critically important as this case developed. So this turned out to be the area of interest. It's where the electrical equipment and two of the fans were. So fans in that area were the only energized equipment in the entire building. There's one of them. And these are DC motors, variable speed, controllable with an inverter and a control box. This is where it began to get interesting because on the face of it, there shouldn't be a problem. The technology is old. However, the more we looked at it, we came across this particular note in the manufacturer's material for the inverter. Be sure to maintain the specified clearance around the inverter and to provide adequate ventilation. Otherwise, the inverter may overheat and cause equipment damage or fire. Well, that's interesting. Now, interestingly, you have to remember that this component was incorporated by the manufacturer of the fan as part of their control system. So let's take a look at what the fan manufacturer did with this instruction and that component. Well, there we go. Some of you I saw were not taking notes, so let's go back one. Now you'll recognize the importance of, look what's pointed out in red. What are the dimensions there? Got it, 8 by 13. There's the actual one, and on the right are the dimensions that we found. 7 by 5, not even close. But wait, there's more. When we open this up to examine the interior of this component, what we find, the fan on the left, you see the RTV, the silicone adhesive that's used there? That's not there from the manufacturer. That was placed there, it turns out, in deposition information from the manufacturer of the fan again, because in preliminary testing, they were finding that some of those components vibrated and vibrated loose. So they just added some RTV. And you'll notice as the slide points out, the inverter chip is right at the bottom here. So let's take a look, a deep dive into the inverter chip. This is its exterior. We never did open it up, but we did run a CT scan on it. The yellow circles, it's a little faint on the screens there, but they portray two areas in that inverter chip that we can see that the connections are completely deteriorated. Got some nice causation shaping up. So what are the key steps? We identified the fans as a likely origin and cause. They were in the place where it was first observed. Now we understand why that was a potential. We looked at exemplars, and in our business, an exemplar means you go back to Walmart and buy another product of exactly the same thing and same make and model, and ran tests. We reviewed scads of discovery material, product literature, depositions of people, of the manufacturers of the fans and the inverter, and we performed extensive testing in our laboratory. We also had the plastics tested by our polymer scientists to evaluate their suitability for the job. We looked at alternate hypotheses that were being offered by other parties and basically ruled them out. It didn't make sense with all of the rest of the information. Final hypothesis: a poor design of that fan led to an overheated drive, failure of a capacitor and an inverter chip, and ultimately the fire. So when we put it together in a very court-like setting, the key experts create reports, they fit together and present and support the hypothesis that we've developed along the way, and these are not standalone. They are going to be critically scrutinized by opposing attorneys and opposing experts. We know because that's what we do as part of our job as well, looking at the opposing experts. The legal team must defend experts to prevent and defend Dober challenges. That's a term of art in our business. Famous case about 25 years ago where the experts were proven by the courts not to have sufficient knowledge and background and the work that they did for that case. So when they bring a challenge, It's called the Doe-Bear Challenge, trying to eliminate the expert. So we've come full circle. Why are experts used at trial? Fundamentally, it's pretty simple. Somebody has to explain in a lucid, understandable, storytelling kind of a fashion what happened. And importantly, what was the role of the parties in the failure? Obviously, this gets massaged by all of the attorneys and by case law, but that's the role of a forensic engineer. I'd be glad to talk questions or any other comments. That parenthetically is a lot to cover. But yeah.